You have always believed light and matter are two separate things. Light lets you see. Matter is what you can touch. One is weightless, the other is solid. But what if I told you that pure light, with nothing added, can become a particle of matter? Not as metaphor, literally. Two beams of light meeting in empty space can give birth to an electron, and this was confirmed in a laboratory. Before we drift deeper into this quiet mystery, whisper in the comments where you are watching from and what hour glows on your clock. If this slow journey through the universe helps you rest, a gentle like and subscribe lets us keep building these worlds for you. Before we go any further, let us return to where you are right now. You are lying somewhere quiet. Perhaps the lamp beside you is on, casting a soft yellow circle across the wall. Perhaps your phone glows faintly in your hand. Perhaps the screen of whatever device is carrying my voice is the only light in the room. Whatever the source, light is touching you in this moment. And somewhere within reach, there is matter. The pillow under your head, the blanket draped across your body, the cool surface of a glass of water on the nightstand. Two things. One you see by. One you rest against. They have always felt like two different categories of being, have they not? And here is the first thing I want you to know. That feeling is not wrong. That feeling is not a mistake of your senses or a failure of your education. That feeling is the conclusion humanity itself reached for nearly all of recorded history. For thousands of years, the brightest minds our species ever produced looked at the world and arrived at exactly the same answer you arrived at without trying. Light and matter are not the same thing. They cannot be. They behave differently. They feel differently. They are different. So before we begin to dismantle that belief, let us honor it. Let us walk back through the long, quiet centuries when this separation was not just a guess, but a truth defended by every careful observer who ever looked up at the sun. Imagine, for a moment, a person standing on a Mediterranean shore around 400 years before the Common Era. The sun is rising. They feel its warmth on their skin. They watch the light scatter across the surface of the water in 1,000 bright fragments. And they wonder, what is this thing that pours from the sky and warms the stones beneath their feet? They cannot hold it. They cannot weigh it. It does not fall like rain. It does not settle like dust. Yet it arrives. It is here. It is real. This was the puzzle that haunted the earliest philosophers. The Greeks were the first to formalize the question, though they were certainly not the first to ask it. Empedocles, who lived in the 5th century before the Common Era, suggested that light was a substance that flowed out of the eye. He believed vision happened because beams emitted from inside the human body reached outward and touched the surfaces of distant things. Light, in his view, belonged to the seer, not to the seen. Think about that for a moment. Think about how reasonable it sounds when you first hear it. You look at a tree across a field, and something connects you to that tree. Something carries your attention there. Why not assume that something travels from you outward, like an invisible finger reaching across the air? The eye, Empedocles thought, was a kind of lantern. The world was lit because we were the lanterns. Plato adopted a version of this idea. He believed there was an inner fire inside the eye that combined with the outer fire of the sun to make vision possible. His student Aristotle disagreed. Aristotle proposed that light was not a substance at all, but a quality of the air between you and the object you were looking at. When the air was activated, vision was possible. When it was not, the world stayed dark. None of these thinkers, as different as their answers were, ever suggested that light might be made of the same stuff as a rock or a piece of wood. To them, light was something else entirely. A signal, a medium, a property, never a thing you could pick up. The Arab scholar Ibn al-Haytham, working in Cairo around 1,000 years ago, gave us the first version of an explanation that modern physics would recognize. He argued that light moves from luminous objects to the eye, not the other way around, and he conducted careful experiments with dark rooms and pinholes to prove it. He laid the foundations of optics as a real science. But even Ibn al-Haytham did not believe that light was a substance like ordinary matter. He believed it was something far stranger, something that traveled, something that could be bent and reflected, something that obeyed rules, but not something that had weight, not something that you could weigh on a scale or hold in your palm. And so the centuries passed. Scholars argued, theories shifted, but underneath all of the disagreement, there was a quiet, shared assumption. Whatever light was, it was not the same kind of thing as your hand or your shoe or the bread on your table. There were shining things, and there were solid things, and these two kinds of things lived in different categories of reality. Now let me take you forward in time. The year is 1666. A young man, only 23 years old, has retreated to his mother's farmhouse in the English countryside because the plague has closed his university. His name is Isaac Newton, and in the quiet of that rural year, in a room he has darkened with thick curtains, he is about to do something that will sound modest and turn out to be revolutionary. He has placed a small glass prism in a narrow beam of sunlight coming through a tiny hole in the shutter, and he is watching the wall on the opposite side of the room. There, projected against the bare plaster, is a band of color: red, orange, yellow, green, blue, indigo, violet, the rainbow itself, pulled out of plain sunlight and pinned to a wall. Newton stares at it. He moves the prism. He passes the light back through a second prism and watches the colors recombine into white. And he thinks, and he writes, and he proposes something bold. He says that light is made of tiny, indivisible particles. He calls them corpuscles. Each color, he believes, corresponds to a different size or weight of corpuscle. White light is simply a mixture of all of them traveling together. This is the first formal moment in scientific history when someone suggests that light might have a kind of substance, that it might be made of pieces, that it might be, in some faint way, like matter. But notice the word he used: corpuscles, not particles of matter, not atoms of light, corpuscles, a word he borrowed from older philosophical writing to describe something tiny and special and not quite ordinary. Newton did not believe that his corpuscles were the same as the atoms that made up wood or water or human skin. He believed they were their own thing, a separate category, smaller than ordinary matter, faster than ordinary matter, capable of passing through glass and water in ways ordinary matter could not. They were like matter, but not really matter. Even the man who first suggested that light might have particles still treated those particles as a separate kind of being. Now imagine the warmth of this older worldview settling over your shoulders like a familiar coat. There is the solid world, the world you can touch, the weight of a stone in your palm, the smooth grain of a wooden table under your fingertips, the cool resistance of a metal spoon. And then there is the shining world, the flicker of a candle on a wall, the shimmer of moonlight on water, the pale gold of a sunrise. Two worlds, two textures of existence, two ways for reality to show itself. This view ruled science for over 100 years after Newton. His authority was so vast, his reputation so towering, that almost no one dared to disagree out loud. Light is corpuscles. Light is particles. Light is a thing apart. But here is where the story turns. Because while Newton was alive, another scientist, a Dutchman named Christian Huygens, had already proposed a completely different idea. Huygens looked at the way light bends when it passes from air into water. He looked at the way it spreads out when it leaves a small opening, and he said no. Light is not a stream of tiny bullets. Light is a wave. It travels through some invisible medium the way ripples travel across the surface of a pond. Think about that image for a moment. You drop a pebble into still water. From the point of impact, circles spread outward, rings expanding in every direction. The water itself does not travel outward. Only the pattern moves, only the disturbance. Huygens believed light worked the same way. Some invisible something filled all of space, and light was simply a series of ripples traveling through that something. He even gave the something a name. He called it the luminiferous ether, the light-bearing ether, an invisible ocean filling the universe, carrying light from the sun to your eyes, the way water carries waves from a pebble to the shore. For more than a century, these two ideas stood in opposition. Newton's corpuscles on one side, Huygens's waves on the other. Both ideas were defended by serious thinkers. Both ideas could explain some experiments. Neither idea could explain all of them. And the strange truth, which no one alive at the time could have known, was that both ideas were partly correct and both ideas were partly wrong. The wave theory won its first decisive victory in the year 1801. A British scientist named Thomas Young performed what would become one of the most famous experiments in the history of physics. He took a single beam of light and passed it through two narrow slits cut into a screen. Behind that screen, he placed a second screen to catch whatever came through. And what he saw changed the way humanity thought about light. If light were made of particles, like Newton had said, then you would expect to see two bright bands on the second screen. One band lined up behind each slit. The particles would travel in straight lines, pass through the openings, and land on the wall behind in two simple shapes. That is not what Young saw. What Young saw was a pattern of many bright and dark bands alternating across the screen. Bright, dark, bright, dark, bright, dark. A striped pattern that looked exactly like what happens when two sets of ripples on a pond meet and interfere with each other. Where the peaks of one wave meet the peaks of another, the water rises higher. Where the peaks of one wave meet the troughs of another, the water flattens. The same logic applied to light could explain the bands. Bright bands where the light waves added together. Dark bands where they cancelled each other out. This was something particles could not do. Particles do not interfere. Particles do not cancel each other out. Particles arrive at one spot or another, and that is the end of the story. Only waves create interference patterns, and so the conclusion seemed inescapable. Light was a wave. Newton, for all his genius, had been wrong. For most of the 19th century, the wave theory ruled. Scientists refined it. They measured the speed of light with greater and greater precision. They studied how light bent and reflected and scattered. They built telescopes and microscopes that depended on treating light as a wave. They confirmed Huygens again and again, and they kept searching for the invisible ether that was supposed to carry these waves, because if light was a wave, then there had to be something it was waving in. Sound waves need air to travel through. Water waves need water. So light waves should need something too. The search for the ether became one of the great quests of 19th century physics. Brilliant experimenters built more and more sensitive instruments, trying to detect the motion of the Earth through this invisible ocean. They reasoned that if the Earth was moving through the ether, then light should travel slightly faster in one direction than another, the way a swimmer moves faster going downstream than upstream. They built devices to measure this difference. They ran the experiments, and they found nothing. The light traveled at exactly the same speed in every direction. The ether refused to reveal itself. But notice what was happening underneath all of this work. Notice the quiet shared assumption that connected every theory, every experiment, every measurement. Whether scientists believed light was a wave or a particle or something stranger, they all agreed on one thing. Light was not matter. Light was something else, something separate. Something that interacted with matter, that bounced off it, passed through it, warmed it, illuminated it. But light itself was not the same kind of stuff as the matter it touched. This belief was so deep, so foundational, so obvious, that no one even questioned it. It was the bedrock under everything else. Light over here, matter over there, two columns of reality, two categories of being, the shining things on one side, the solid things on the other, and a clear, bright line drawn between them that no serious thinker would have dreamed of crossing. For hundreds of years, this separation seemed obvious, almost sacred. The way the seasons are separate from the soil, the way music is separate from the instrument that plays it, the way meaning is separate from the page it is written on. Light and matter belong to different worlds. They cooperated, they interacted, but they were not, they could not be, the same thing. So let yourself rest in that view for a moment. Let yourself remember what it feels like to live inside it. The lamp on your nightstand is producing light. The wood of the nightstand is matter. The light bounces off the wood. The light enters your eye. The light tells you the wood is there, but the light is not the wood. The wood is not the light. They are partners in the simple act of seeing, but they are not the same. This is the world your senses still report to you. This is the world your intuition still defends. And for thousands of years, it was also the world your most brilliant ancestors confirmed for you. But now, very softly, listen for something else. In the year 1879, in the German city of Ulm, a child was born to a Jewish family. He did not speak fluently until late. He struggled in school not because he was unable, but because he was unwilling to be told what to think. He grew into a quiet, stubborn young man with thick dark hair and large, gentle eyes. He tried to find work as a university teacher and could not. He took a job in a small office in the Swiss city of Bern, examining patent applications for inventions submitted by other people. He worked there for hours each day, processing forms, stamping papers, evaluating designs, and in the spaces between his official tasks, he scribbled equations on scraps of paper. He read physics journals in the evenings. He thought constantly about light. His name was Albert Einstein. He was 26 years old. He had no laboratory. He had no graduate students. He had no funding and no institutional support. He had only a desk in a patent office and a head full of questions that no one had yet been brave enough to ask. And in the single year of 1905, working alone in his free time, he was about to publish a series of papers that would shatter the long, quiet separation between light and matter that humanity had defended for over 2,000 years. The wall between the shining things and the solid things was about to fall. But not yet. Not in this part of our story. For now, let yourself remain inside the older world. The world where light is one thing and matter is another. The world where the lamp on your nightstand and the wood it sits on are forever distinct. The world that was about to end without knowing it, because in a patent office in Bern, a tired young man was lifting his pen. Let us stay with him for a moment. Albert Einstein, sitting at his desk in the Federal Office for Intellectual Property in Bern, Switzerland. The year is 1905. He is 26 years old. His hair is not yet white. His face has not yet become the most recognizable face in the history of science. He is simply a young man in a modest office, doing a modest job in a modest city that has no idea what is sitting inside one of its buildings. The work is not glamorous. Patent applications arrive on his desk in stacks. Someone has invented a new kind of valve. Someone else has designed a better mechanical clock. Someone has submitted plans for an improved electrical relay. Einstein reads each proposal carefully, thinks about whether it is genuinely novel, writes his assessment, stamps the paper, moves on to the next one. He is good at this job. His supervisor has noted that he processes applications quickly and accurately. He has a practical mind. He can see through a description to the physical reality underneath it. But there is another Einstein living inside the first one. The one who stamps the patents, leaves the office each evening, and goes home to a small apartment where the equations are waiting, where the questions are waiting, where the universe is waiting to be understood by someone patient enough to sit with it in the quiet and refuse to look away. He has no laboratory. This is important to understand. Einstein in 1905 is not a man in a white coat surrounded by instruments. He is a man with a pencil and paper and a mind that will not rest. His experiments are conducted entirely in the space behind his eyes. He calls them thought experiments. He imagines scenarios. He follows the logic wherever it leads, even when it leads somewhere that makes no sense according to everything physics has said before. And in this particular year, the year that his colleagues would later call his miracle year, he publishes not one but 4 papers that change the direction of human knowledge. 4 papers in 1 year. While working full-time as a patent clerk, each paper would have been the crowning achievement of most scientific careers. Together, they represent something that has almost never happened in the history of human thought. A single mind, in a single year, rewriting the rulebook of reality. We are going to focus on 2 of those papers tonight, because between them, they contain the key to everything that follows. Between them, they contain the answer to the question you are lying here with. How can light become matter? Why is it possible? The answer was already written down in a patent office in Bern in the year 1905. It just took the rest of the world a long time to understand what had been said. The first paper is about light. Specifically, it is about something that had been bothering physicists for years. A strange and stubborn experimental result called the photoelectric effect. And the reason it matters to our story is that it was the first time anyone proved with hard evidence that light is not simply a smooth, continuous wave. That light, in fact, arrives in pieces. Here is what the photoelectric effect is, in plain terms that do not require any prior knowledge. If you take a metal surface and shine light on it, sometimes electrons jump off the surface. The light knocks electrons loose. You can detect these electrons, count them, measure the energy they carry when they escape. This is not a theory. This is an observation that had been confirmed in laboratories many times. Light hits metal, electrons fly off. This happens. The strange part was what happened when you adjusted the light. When physicists dimmed the light, fewer electrons came off. That made sense. Less light, fewer electrons. Fine. But when they used a lower frequency of light, a redder, longer wavelength light, something unexpected happened. Not fewer electrons, no electrons at all. The light could be as bright and intense as you wanted. If the frequency was too low, nothing came off. 0 electrons, as though the light simply was not energetic enough to do the job, no matter how much of it you used. And when they used higher frequency light, the electrons that flew off carried more energy. Not more electrons, more energetic electrons. The brightness of the light changed how many electrons came off. The frequency of the light changed how much energy each individual electron carried when it left. This is very strange if you believe light is a continuous wave. Think of a wave on the ocean hitting a beach. If you want to knock a pebble up the slope, you need a big enough wave. You can have 1,000,000 tiny ripples, but if each ripple is too weak, the pebble stays where it is. What matters is the height of each individual wave, not the total amount of water. Now think about light in the same way. What the experiments were suggesting was that each individual unit of light carried a specific amount of energy determined by its frequency. And that energy was either enough to knock an electron free, or it was not. No amount of low-frequency light could do the job that a single particle of high-frequency light could do. Einstein looked at this data, and he made a claim that was radical enough that it took 17 years and a Nobel Prize for the scientific community to fully accept it. He said light does not travel as a continuous wave. Light travels in discrete packets, individual units, each unit carrying a fixed amount of energy determined by its frequency. He borrowed a word that the physicist Max Planck had recently used in a different but related context. He called these packets quanta. A single packet of light would later be given the name photon. Now, let me give you a way to feel this, not just understand it. Imagine it is raining. You are standing at a window watching the water fall. If you believe the older view, light as a wave, then rain is the right analogy. Water falls continuously from the sky. A sheet of water, unbroken and smooth. You cannot point to where one drop ends and the next begins because it is all just water, arriving as a single entity. But Einstein is saying something different. Einstein is saying that rain does not fall as a sheet. Rain falls as individual drops. Each drop separate, each drop with its own size and weight. Some drops heavier than others. When a drop hits the window, it leaves a specific small impact. And if the drops are too light, too small, they will not dislodge the pebble of paint beginning to flake off the corner of the sill. It does not matter how many small drops fall. Only a drop above a certain weight will do the job. This is what Einstein showed. Light is not a sheet of water. Light is rain, individual drops, individual packets. And the weight of each drop, the energy of each photon, is determined by its frequency. Violet light carries heavier drops than red light. That is why violet light can knock electrons free from surfaces that red light cannot touch, regardless of how bright the red light is. This was a crack in everything that had come before, because if light arrives in discrete packets, then in some strange but undeniable sense, light has a kind of grain to it, a kind of structure, a kind of individuality that waves do not have. Waves are continuous. Waves blend into each other, but packets do not blend. Packets are separate. Packets are units. Packets are, in a word, that carries enormous weight, particular. The wave theory of light had seemed so secure. Young's double-slit experiment had seemed so conclusive. And yet here was inescapable experimental evidence pointing the other way. Light behaves like a wave in some experiments. Light behaves like particles in others. Both sets of experiments are real. Both sets of results are correct. And the universe, apparently, does not care that this makes no sense according to any framework any human being had ever constructed. This is the first crack. This is the hairline fracture running through the clean separation between light and matter. Because matter is made of particles. Matter is discrete. Matter comes in units you can count. Atoms, electrons, protons, things that are either there or not there. And now, light, which was supposed to be the other thing, the continuous, smooth, shining other thing, is revealing that it too has a discrete side, a grainy side, a side that arrives in countable units. But the deeper crack, the one that changes everything, came from a different paper in that same year. A paper that is the most famous equation in all of human knowledge, carried by almost everyone who has ever attended school, understood by almost no one who has ever attended school. 4 symbols, 1 equals sign. And an idea so strange, so far outside ordinary human intuition, that it took decades for its full implications to be believed. Energy equals mass times the speed of light squared. E equals mc squared. Let me stay with this for a moment, longer than you might expect, because I do not want to rush past it the way we often do when a famous thing has become too familiar to see clearly. I want you to actually feel what this equation is saying, because what it is saying is not just useful physics. What it is saying is one of the most astonishing claims ever made about the nature of reality. Mass and energy are not two different things. They are two forms of the same thing. That is the entire sentence. That is everything. That is the crack that splits the old world open. Mass and energy are not two different things. They are two forms of the same thing. Think about what mass is. Mass is the property of matter that makes it resist being pushed around. Mass is what you feel when you lift a stone. The heaviness, the inertia, the stubborn insistence of the stone on staying where it is unless you apply a force. Mass is the signature of matter. Mass is what makes matter, matter. And think about what energy is. Energy is the capacity to make something happen. A stretched spring has energy. A raised boulder has energy. A burning fire has energy. A ray of sunlight has energy. Energy is not a thing you can hold, not a substance you can bottle. Energy is a property, a capacity, a potential waiting to become action. These two things, mass and matter on one side, energy and light on the other, are the same thing, not similar things, not related things, the same thing, wearing different clothes. Now, let the speed of light squared do its work on your understanding. The speed of light is approximately 300 million meters per second. That is already a number that resists imagination. Light travels from London to New York in about 18 milliseconds. It circles the entire Earth 7.5 times in a single second. It covers the distance from the Earth to the Moon in about 1.25 seconds. The speed of light is a number so large that your nervous system has no reference point for it. Now, square that number. Multiply 300 million by 300 million. The result is 90 quadrillion, 90,000 million. Written out, it looks like this. 90, followed by 15 zeros. That number is the conversion factor between mass and energy. That is the exchange rate. And it means that a tiny, almost impossibly tiny amount of matter contains a staggering amount of energy locked inside it. 1 gram of matter, the mass of a small paperclip, the mass of a few drops of water. 1 gram of matter, if it could be completely converted into energy, would release approximately 90 terajoules of energy. That is roughly the explosive yield of a large nuclear bomb. 1 paperclip, fully converted, could level a city. This is why nuclear weapons work. They do not convert all of their mass into energy. They convert a small fraction of it, a fraction of 1%. And still, the result is catastrophic. Because the number you are multiplying by is so incomprehensibly large that even a small fraction of a small mass becomes an enormous amount of energy. Now feel the equation running in the other direction. Because this is where the story you are following tonight begins to come into focus. Einstein did not say energy comes from mass. He said energy equals mass times a constant. An equation runs both ways. If mass can become energy, then energy can become mass. If the matter in the paperclip contains 90 terajoules locked inside it, then 90 terajoules of energy, given the right conditions, contains within it a paperclip's worth of mass waiting to be born. A pebble is frozen energy. Say that again and let it sit in your chest for a moment. A pebble is frozen energy. The cold, smooth stone you might pick up on a beach and turn over in your fingers is not simply dead matter. It is an enormous amount of energy that has taken on solid form. The mass is the energy. They are the same thing, one wearing the coat of solidity and the other wearing the coat of activity, but underneath the coats, the same. And a flame is matter unwinding. When wood burns, a small amount of its mass is converted into light and heat. A small fraction of the solid matter in the wood reaches out of its frozen state and becomes energy again. Every fire you have ever seen is a tiny demonstration of the equation. Every burning candle on every birthday cake is mass becoming energy, matter becoming light, the solid world releasing a little of itself back into the shining world. The wall between the solid things and the shining things is not a wall, it is a doorway, and the equation tells you the price of the passage through it. Now let us reverse the implication one more time, carefully, almost reverently, because this is the moment the rest of our story has been building toward without announcing it. If matter can become energy, if the stone contains frozen energy waiting to be released, then the reverse must also be possible. Energy can become matter. Light, which is energy, can become matter. Given enough energy concentrated in the right way, in the right place, new matter can appear where there was none before, not from another piece of matter, not by rearranging existing atoms. New matter, summoned from pure energy, from a beam of light. This is not science fiction. This is not metaphor. This is the logical consequence of the most tested and verified equation in the history of physics. An equation derived by a tired 26-year-old in a patent office, scribbled in the margins of his real life, published in a journal that most of the physics community read with cautious skepticism. But the equation does not care about skepticism. The equation does not care about whether it seems reasonable or whether it fits inside the comfortable frameworks of older thinking. The equation simply is. It simply states a truth about the universe, that the universe has been demonstrating all along, whether or not any human being was watching or believed or understood. Energy equals mass times the speed of light squared, both directions, always, without exception. The question that remained, the question that would take another 3 decades to even be formally posed, and nearly a century to be experimentally confirmed, was this: what is the minimum amount of energy you need, concentrated in the right way, to make matter appear from nothing? And is light, specifically photons, capable of doing this on their own? You already know the answer, because you heard it in the first words of our story tonight. But the path from Einstein's patent office in 1905 to a particle detector in New York in 2021 is not a short one. It is a path paved with strange mathematics and stranger experiments, and the slowly dawning realization that the universe is far more fluid, far more interconnected, far more unwilling to respect the clean categories we draw around it than anyone comfortable in the older world would ever have wanted to believe. The universe was about to be caught doing exactly what Einstein's equation promised it could do, and the catching of it would take some of the most extraordinary minds and machines the human species has ever produced. But for now, let the equation rest in your body the way a stone rests in a palm. E equals mc squared. Energy is mass. Mass is energy. The shining things and the solid things are one thing. The lamp on your nightstand and the wood it sits on are, in the deepest sense, made of the same underlying reality. One form is just frozen, and one form is moving. And the universe has always known how to go from one to the other. It was about to show us. Close your eyes for a moment, or do not close them. Let them rest on whatever soft surface they have found in this quiet hour, and imagine space, not outer space specifically, though we will get there. Just space, the idea of space, the idea of a region where nothing is. Imagine the gap between two stars, the vast cold darkness between them. No planets, no dust clouds, no light passing through at this particular moment. Just distance, just emptiness, just the absence of things stretching on for light years in every direction. This is what we call a vacuum. This is what the word empty means when physicists use it. A region containing nothing. Now hold that image, because everything you just imagined is wrong. Not wrong in the way a careless mistake is wrong. Wrong in the way that the Earth being flat seemed obvious and turned out to be the surface of something spherical beyond the horizon of ordinary sight. Wrong in a way that required entirely new mathematics, an entirely new experimental technology to even begin to correct. Wrong in a way that, once corrected, changes not just the answer, but the nature of the question. Empty space is not empty. The vacuum is not a void, and the silence between atoms is not silent at all. It is, in fact, the loudest place in the universe, if by loud we mean the most activity, the most constant creation and destruction, the most relentless churning of something from nothing and back again. Every cubic centimeter of what you think of as empty space is, at this moment, seething with energy, popping with fleeting events, alive with what physicists call the quantum vacuum and what we might simply call the hum beneath everything. This is not a poetic metaphor. This is the most precisely tested theory in the history of human science. Quantum electrodynamics, the framework that describes how light and matter interact at the deepest level, has been confirmed experimentally to an accuracy of better than 1 part in a billion. When its predictions about the behavior of electrons are checked against measurement, the agreement is so precise that it is the equivalent of measuring the distance from New York to Los Angeles and being accurate to within the thickness of a human hair. This is the most accurate theory we have ever constructed. And this theory says, without ambiguity, that empty space is not empty. But let us arrive at that conclusion slowly, the way it was arrived at historically, because the path is part of the understanding. We left Einstein in 1905 with his equation, energy equals mass times the speed of light squared. We understood that mass and energy are two forms of the same thing. We understood that light, which is energy, contains within itself the latent possibility of becoming matter. But to understand how that transformation actually happens, we need to go deeper. We need to go underneath the surface of matter and light and find out what they actually are at the most fundamental level. We need to go to the place where the real physics lives, below atoms, below electrons, below even the neat particle picture that the word photon might suggest. We need to talk about fields. Start with the word field and give it the plain language translation it deserves before the technical version obscures it. A field, in physics, is a quantity that has a value at every point in space. Temperature is a field. Right now, somewhere in the room or space where you are listening, there is a temperature value. It might be different at the ceiling than at the floor. It might be warmer near the lamp and cooler near the window, but at every single point in the room, at every precise location in three-dimensional space, there exists a temperature value. The temperature field fills the room completely. There is no gap in it, no region where temperature simply does not exist. It covers everything. Now imagine a much more fundamental kind of field. Not temperature, which is a property of matter, but a field that exists everywhere in the universe. Not because matter is there, but because the field itself is a fundamental feature of reality. A field that would exist even if there were no planets, no stars, no atoms, no observers. A field that fills the void between galaxies the same way it fills the space between the pages of the book on your shelf. This is what quantum field theory proposes, that the universe is not, at the most fundamental level, made of particles. The universe is made of fields. Particles are not the basic units of reality. Fields are, and what we call particles are simply disturbances in those fields, ripples, vibrations, concentrated excitations of energy in an underlying field that is always there, whether it is vibrating or not. Let me give you the analogy that will carry you through this section. Imagine a lake on a perfectly calm day. The surface is still. You could look at it and say, there is nothing happening here. And in a sense, you would be right. No waves are crossing the surface. No boat has recently passed. The water is flat. But is the lake empty? Of course not. The water is still there. The lake itself is still there. Its capacity to ripple, to wave, to carry disturbances from one shore to another is still there. It is simply at rest. Now imagine disturbing that surface. You drop a stone. Immediately, rings of ripple spread outward from the point of impact. The lake, which was flat and seemingly empty of events, has now produced a real physical phenomenon. A pattern of movement traveling across the water, carrying energy, capable of reaching the opposite shore and causing further effects when it arrives. That traveling pattern is, in a very real sense, an entity. It has a location, it has energy, it has a direction, it has properties you can measure, and yet it is not made of anything new. The lake was always there. The field was always there. The ripple is simply the field doing something it always had the capacity to do. This is what a particle is. A particle is not a tiny pellet of solid stuff flying through empty space. A particle is a ripple in a field. An excitation, which is the technical word, meaning a disturbance or vibration in an underlying field that fills all of space. When we say an electron exists at a certain location, what we mean, in the language of quantum field theory, is that the electron field has a localized excitation at that location. When we say a photon is traveling from the lamp on your nightstand to the wall of your room, what we mean is that the photon field, the electromagnetic field, has a traveling excitation moving in that direction. The electron field fills the entire universe. Every point in space, including the most remote and empty regions between the galaxies, has an electron field value. Most of the time, most places, the field is at its ground state, which simply means it is not vibrating. The lake is calm. But where there is an electron, the field is excited. It is doing something. It is carrying a ripple. The same is true of every other fundamental particle we know of. There is a photon field, and photons are its excitations. There is an electron field, and electrons are its excitations. There is a quark field, a muon field, a Higgs field, each one filling all of space, each one capable of being excited into the particle we have named, each one sitting quietly in the background of reality, waiting when the field is undisturbed. Now here is where the deep strangeness begins. Because when we say the field is at its ground state, when we say the lake is calm, we mean something very different from what we would mean if we were talking about a classical system. In classical physics, ground state means zero. It means nothing is happening. It means the energy of the system is at its lowest possible value, which is zero. The lake is perfectly flat. No movement, no energy, nothing. But quantum mechanics does not allow this. Quantum mechanics has a rule, derived from the work of Werner Heisenberg in the 1920s, that forbids perfect stillness. It forbids zero. This rule is called the Heisenberg uncertainty principle. And I want to introduce it to you not as a formula, but as a statement about the nature of reality itself, because that is what it actually is. The Heisenberg uncertainty principle says that certain pairs of properties cannot both be precisely defined at the same time. Position and momentum, energy and time. The more precisely you know one, the less precisely you can know the other. Not because your instruments are not good enough, not because you have not measured carefully enough, but because reality itself does not allow both values to be simultaneously exact. This is not a limitation of human knowledge. It is a feature of how the universe is built. Now apply this to the quantum field. If a field were in a perfect ground state, if it had exactly zero energy and were perfectly still, then both its energy and the rate of change of its energy would be simultaneously and exactly defined. They would both be exactly zero, but the uncertainty principle forbids this. You cannot know both values precisely, which means the field cannot be exactly zero. The field must fluctuate. It must wobble. It must, at every point in space, at every moment in time, be doing something, not much, not producing full particles, but something. A restless background trembling that can never be fully silenced. This is the quantum vacuum. This is the ground state of all the fields that fill the universe. Not nothing, not silence, a constant, irreducible, mathematically necessary trembling, the hum beneath everything, the lake that looks calm but is, if you look closely enough, covered in the faintest possible ripples, too small to see with any ordinary instrument, but absolutely, measurably, provably there. And these fluctuations do something extraordinary. They produce what physicists call virtual particles. Let me translate that term carefully, because it is often misunderstood, and the misunderstanding matters. A virtual particle is not simply an imaginary particle or a particle we cannot see. A virtual particle is a brief, temporary excitation of a quantum field, one that appears and disappears so quickly that it cannot be directly detected as a particle, but that nonetheless has real, measurable physical effects on the world around it. Think of it this way. The quantum vacuum is constantly borrowing energy from the universe, using that energy to briefly create a pair of particles, one particle and its corresponding antiparticle, and then returning that energy by allowing the pair to annihilate each other. The borrowing and returning happens so fast, in such a brief slice of time, that the uncertainty principle permits it. If the duration is short enough, the energy uncertainty is large enough to allow the transaction. The universe can, in a sense, write a very short-term check, use the energy, and pay it back before anyone notices. This sounds absurd. It sounds like something from a story, not from physics. But there is a beautiful piece of evidence that confirms it directly, an experiment you can perform on a tabletop that proves the quantum vacuum is real and active and full of these fleeting events. The experiment is called the Casimir effect, and it was predicted by the Dutch physicist Hendrik Casimir in 1948 and confirmed experimentally in 1997. The setup is almost comically simple. Take two flat metal plates and place them facing each other in a vacuum, extremely close together but not touching. There is nothing between them. No air, no gas, no substance of any kind, just space. According to classical physics, nothing should happen. Two neutral plates in a vacuum experience no force. There is nothing to push them together or pull them apart. But quantum mechanics says otherwise. And quantum mechanics is right. The two plates are pushed together by a tiny but measurable force. They attract each other. Something in the vacuum between them is producing a real physical pressure. Here is why. Virtual particles are being produced everywhere in the vacuum, including in the space between the plates. But the space between the plates is limited. It is a small gap. And The virtual particles that can exist in a small gap are restricted to those whose wavelength fits within the gap. Certain wavelengths are excluded, the way certain notes cannot be played on a string that is too short. Meanwhile, outside the plates, all wavelengths of virtual particles are present. The vacuum outside the plates is richer, more energetically dense than the vacuum between them, and this difference in pressure, outside being higher than inside, pushes the plates together. This is not a theoretical prediction waiting for confirmation. This has been measured. The force has been quantified. It matches the quantum mechanical prediction with extraordinary precision. The Casimir effect is physical proof that the vacuum is not empty. Virtual particles are not just a mathematical convenience. The fluctuations of quantum fields are real. The trembling of the ground state of the universe is real. Empty space is not empty, and the evidence for this sits on laboratory benches in physics departments all over the world. Now let us go back to the fields themselves. Back to the electron field and the photon field and all the other fields that fill the universe. Because here is something crucial that the outline of quantum field theory makes possible, something that brings us one step closer to the transformation at the heart of our story. The fields are not isolated from each other, they interact. They are coupled, which in physics means they can exchange energy with each other, they can influence each other, they can, under the right conditions, convert excitations from one field into excitations of another. Imagine our lake again. But now imagine two lakes sharing a shoreline, separated by a narrow strip of land. A wave traveling across the first lake reaches the shared shoreline. If the strip of land is narrow enough and the wave is powerful enough, the disturbance does not simply stop, it transfers, it crosses the barrier, it produces a new wave in the second lake. Energy from the first lake has now become energy in the second lake. The two bodies of water have exchanged something real. The electron field and the photon field work this way. They are coupled by what physicists call the electromagnetic interaction. When an electron accelerates, it disturbs the photon field. It produces a ripple in the electromagnetic field, which propagates outward as a photon. Light is created. The electron field has poured some of its energy into the photon field, and when a photon is absorbed by a charged particle, the reverse happens. The electromagnetic field loses a ripple. The other field gains energy. This coupling between fields is what makes the physical world possible. It is what allows atoms to emit light when their electrons change energy levels. It is what allows your eyes to see. It is what allows the warmth of sunlight to reach your skin. Every interaction between light and matter that has ever occurred, every photon ever emitted, every photon ever absorbed, every ray of sunlight that has ever fallen on an upturned face, is a story about two fields exchanging energy, about one field pouring its excitations into another. Now here is the question that everything we have covered tonight has been slowly, carefully, inevitably building toward. If the photon field and the electron field are coupled, if they can exchange energy in both directions, if an electron can produce a photon and a photon can be absorbed by an electron, then is there a condition under which a photon, an excitation of the electromagnetic field, can pour enough energy into the electron field to produce not just an absorbed photon, but an entirely new electron, a new particle of matter born from pure light with no prior matter required? The answer, which Einstein's equation already guaranteed before anyone thought to ask the specific question, is yes. Under the right conditions, a photon does not just get absorbed. Under the right conditions, a photon can trigger the creation of a brand new excitation of the electron field. Not just one excitation, two. Because of a rule we have not discussed yet, a rule that governs all particle physics, the rule of conservation of charge, The new excitations must come in a matched pair. One electron carrying negative charge, one positron, which is the antimatter twin of the electron, carrying positive charge. The total charge of the pair is 0, matching the charge of the photon it came from, which is also 0. The books balance. The rules are satisfied. And matter, real tangible matter made of electrons and their counterparts, has appeared from a photon. Light has become matter, but there is a price. A precise and unforgiving price set by that conversion factor we sat with earlier. The speed of light squared. The energy of the photon must be at least large enough to account for the mass of the two particles it produces. 2 electrons worth of mass, converted into energy units using the equation, gives a minimum threshold. Below that threshold, the photon cannot do this. Above it, the transformation becomes possible. And a single photon of ordinary visible light, the kind coming from the lamp on your nightstand, does not carry anywhere near that much energy, not even close. Visible light photons are too gentle, too mild, too soft. The threshold requires photons carrying millions of times more energy than anything your lamp produces, gamma rays. The most energetic photons in the universe. Hard radiation born in the hearts of stars, or the vicinity of black holes, or the first violent microseconds of the universe itself. So the mechanism exists. The coupling between fields makes it real. The equation sets the price. The price is high. And the question becomes not whether this transformation is possible in principle, but whether it can ever be made to happen in practice, in a laboratory, under conditions that human beings can create and control. That question was about to be asked. And asking it would require 2 young physicists, a piece of paper, a quiet afternoon, and a willingness to follow the mathematics somewhere that no experiment at the time could follow them. The mechanism is real. The fields are real. The trembling vacuum is real. And somewhere inside that restless ocean of virtual events, inside the constant whispering between fields, the doorway between light and matter stands quietly open, waiting for something to walk through it. Let us step back for a moment from the mathematics and the fields and the trembling vacuum. Let us return to something you can picture with your eyes closed. Imagine the ocean, a wide grey ocean on a day when the weather is building towards something. 2 storm systems moving toward each other from opposite horizons, each one pushing its own set of waves across the surface. The waves from the east rolling in long dark ridges, the waves from the west rolling in long dark ridges, and somewhere in the middle of all that grey water, the 2 sets of waves are going to meet. When they do, something happens that any sailor knows and any physicist can calculate. The waves collide, their energies combine. For a brief and violent moment, the water at the collision point rises far higher than either wave could have reached alone. A peak forms, a crest of concentrated energy that exists for only a fraction of a second before the waves pass through each other and continue on their separate ways. The ocean settles, the crest is gone, and where it was, the water looks exactly as it did before. Now, imagine that the waves are carrying enough energy, not storm waves, not even tsunami waves, something beyond that, something so concentrated, so violent in its collision, that the peak of energy formed at the meeting point does something that has no equivalent in any ocean on Earth. It does not simply rise and fall. It reaches a threshold. It crosses a line. And from that crest of pure energy, from that fleeting point where 2 waves have given everything they carry to a single location, something appears. Not foam, not spray. Something solid, something that was not there before the waves met and is there after. A fish leaping from the water where there was no fish before the collision. Matter, conjured from the energy of two waves meeting. This is not what ocean waves do, but this is exactly what photons can do. And in the year 1934, two young physicists sat down, picked up their pencils, and calculated precisely when and how and under what conditions the fish would leap. Their names were Gregory Breit and John Wheeler. They were Americans, working in the tradition of the theoretical physics that had been transformed by Einstein and Bohr and Heisenberg and Dirac in the 2 decades before. The field was young. The mathematics was still being built. Quantum electrodynamics, the full theory of how light and matter interact at the quantum level, was not yet in its finished form. But enough of the framework existed that a careful theorist could sit down with paper and ask a specific question and follow the mathematics to a specific answer. The question Breit and Wheeler asked was this: what happens when two photons, two packets of light, collide directly with each other? Not a photon hitting an electron, not a photon being absorbed by an atom. Two photons traveling toward each other, meeting head-on, two waves of light crossing in space. At low energies, photons pass through each other without interaction. Light beams cross and continue undisturbed. You can verify this yourself. Hold up 2 flashlights so their beams cross in the air and watch what happens. Nothing happens. The light goes straight through. Photons, at ordinary energies, are transparent to each other. But Breit and Wheeler were not asking about ordinary energies. They were asking about extreme energies. Photons carrying millions of times more energy than visible light. Gamma-ray photons, the most energetic photons the universe produces. And their question was whether two such photons, meeting head-on with enough combined energy, could do something that no experiment had ever observed, and no physicist had yet formally predicted in this specific way. Could two photons annihilate each other and produce an electron and a positron? Not a photon hitting matter, not nuclear reactions, not any of the particle creation processes that physicists already knew about, all of which required existing matter as a starting point. Pure light meeting pure light, two photons, nothing else. And from their meeting, two particles of matter born where there had been nothing but light before. The mathematics said yes. Let us slow down and understand what the mathematics was actually saying, because the answer is not just yes in a vague and hand-waving way. The answer is yes with specific conditions, specific thresholds, specific conserved quantities that must balance like accounts before the transaction is permitted. First, the energy threshold. Each photon carries energy. The two photons together must carry at least enough combined energy to account for the mass of the two particles they will produce. One electron and one positron. The mass of each is known with extraordinary precision. Using Einstein's equation, the minimum energy required can be calculated exactly. It comes out to approximately 1.022 million electron volts, a unit of energy used by particle physicists that corresponds to the energy an electron gains when accelerated through 1 million volts of electric potential. The two photons together must carry at least this much energy, and they must be oriented so that their energies combine at the point of collision rather than cancelling. Second, the conservation laws. Every particle interaction must obey a set of conservation laws that physics has confirmed in every experiment ever performed. Energy must be conserved, momentum must be conserved, electric charge must be conserved. A photon carries no electric charge. An electron carries negative charge. A positron carries positive charge. Create an electron and a positron together and the total charge of the pair is 0, which matches the 0 charge of the two photons they came from. The books balance. The transaction is legal. Third, the spin. Photons carry a quantum property called spin, and the spin of the particles produced must be consistent with the spin carried in by the photons. The mathematics confirms that an electron and a positron pair can satisfy this requirement under the right collision geometry. The spin books also balance. Everything checks out. The mathematics is clean. The conservation laws are satisfied. Two photons with sufficient energy colliding head-on in the right geometry can and must produce an electron and a positron. The prediction was not a guess or an intuition. It was a derived result, a logical consequence of the equations that had already been confirmed in other contexts. Breit and Wheeler were not inventing new physics. They were following the existing physics to a place no one had yet looked. They published their prediction in the Physical Review in 1934. The paper was careful and precise. The mathematics was correct. And buried in the paper, almost as a footnote to the main result, was an observation that would haunt the prediction for nearly 9 decades. The energies required were so extreme that the experiment, they wrote, appeared to be beyond the range of observation at the present time. At the present time, a phrase that sounds hopeful, a phrase that implies eventually, a phrase that the physicists of 1934 used to soften what was, in practice, a statement very close to never. Think about what it meant to perform this experiment. You need 2 photons, not ordinary photons, gamma-ray photons, each carrying hundreds of thousands or millions of electron volts of energy. You need to fire them at each other with enough precision that they actually collide, that they actually meet at a single point in space at the same moment. And you need to do this not just once, but many times, because the probability of any 2 given photons actually colliding and producing a pair is extremely small. The cross-section, which is the physicist's term for the effective target size of the interaction, is tiny, vanishingly tiny. You need enormous numbers of photon pairs meeting at enormous energies before statistics gives you even a handful of successful transformations that you can detect. In 1934, the most powerful sources of energetic photons available were radioactive materials, small amounts of radium and similar elements emitting gamma rays through natural decay. These sources produced photons with the right energy range, but they were weak, far too weak. The flux of gamma-ray photons from any available radioactive source was nowhere near sufficient to produce collisions in observable numbers. You could wait longer than the current age of the universe and still not see a single Breit Wheeler event from a radium source in a laboratory. There was no laser technology. There would not be a laser of any kind for another 26 years. The first working laser was demonstrated in 1960, and it produced light of optical frequencies, nothing close to the gamma-ray energies required. Particle accelerators, the machines that could in principle create high-energy photons by colliding particles together, were only beginning to be developed in the 1930s. The cyclotron, invented by Ernest Lawrence, was just becoming a real tool for physics. But the energies achievable were still far below what the Breit Wheeler calculation demanded for its purest form. And then the world changed in ways that had nothing to do with physics and everything to do with politics. September 1939, the Second World War. European physics laboratories evacuated, converted, repurposed. Physicists scattered across continents. Some fled to America. Some went into military service. Some worked on radar. Some, in the years that followed, worked on something whose name would become synonymous with the conversion of mass into energy in the most terrible possible demonstration. The Manhattan Project was, among many other things, a crash course in the physics of mass to energy conversion. It confirmed, in the most brutal possible way, that Einstein's equation was correct in the direction from matter to energy. The bombs over Hiroshima and Nagasaki were, at their core, demonstrations of E equals mc squared running in one direction. Tiny fractions of tiny masses of uranium and plutonium converting into energy with catastrophic efficiency. But the direction the world needed to observe for the Breit Wheeler prediction was the reverse. Energy into matter, light into solid particles. And that direction remained untouched. Still only a mathematical prediction, still waiting for technology that did not yet exist. The post-war decades brought a revolution in accelerator technology. Machine after machine was built, each one more powerful than the last. The Cosmotron at Brookhaven in 1952, the Bevatron at Berkeley in 1954, the first proton synchrotron at CERN in 1959. Energies climbed, new particles were discovered, the pion, the kaon, the antiproton. Physicists confirmed that matter could be created from energy in particle collisions, using the kinetic energy of accelerated protons to produce new particles in the debris of violent impacts. Pair production, the creation of an electron and a positron from a single high-energy gamma-ray photon passing near an atomic nucleus, was observed and studied in detail. This was not the Breit Wheeler process. It required the presence of the nucleus to conserve momentum. It was matter-assisted pair production, not the pure light from light version Breit and Wheeler had described, but it confirmed the underlying physics. It confirmed that the electron-positron pair could be born from energy. The door existed. Only the pure version, the two-photon version, the version where no matter was involved at any stage, remained unopened. The laser changed everything, slowly. From 1960 onward, laser technology developed with extraordinary speed. Early lasers were weak and limited. But with each passing decade, the peak power achievable grew. Scientists learned to compress laser pulses in time, to pack enormous amounts of energy into shorter and shorter bursts, creating peak intensities that early laser pioneers would have found unimaginable. By the 1980s, a technique called chirped pulse amplification allowed laser systems to achieve peak powers measured in terawatts and beyond. A terawatt is a million watts. The total electrical generating capacity of the United States is roughly a terawatt. A modern research laser can produce that power for a fraction of a nanosecond in a beam the width of a human hair. With intensities like these, the idea of creating gamma-ray photons intense enough to attempt something related to the Breit Wheeler prediction began to shift from impossible to merely extremely difficult. And in 1997, at the Stanford Linear Accelerator Center in California, an experiment called E144 did something that brought the prediction closer than it had ever been to reality. The experiment was elegant in its design and careful in its execution. The Stanford Linear Accelerator was one of the longest and most powerful electron accelerators ever built. It could accelerate electrons to nearly the speed of light, giving them energies of around 47 billion electron volts. In the E144 experiment, a powerful laser beam was fired head-on at this beam of ultra-high-energy electrons. The photons from the laser, meeting the electrons moving at nearly the speed of light, underwent a process called inverse Compton scattering. The collision between the laser photons and the fast-moving electrons boosted the photons to extraordinarily high energies, creating a beam of gamma-ray photons far more energetic than any laser alone could produce. These gamma-ray photons then interacted with additional laser photons following behind them, and in the detectors, electrons and positrons appeared. Matter was created from photons and electrons colliding. The books balanced. The conservation laws were satisfied. The energies were consistent with the predictions. But this was not the pure Breit Wheeler process. This was close. This was a demonstration that the underlying physics was real, and that high-energy photon interactions could produce matter. But the E144 experiment, involved more than just two photons meeting in pure empty space. It involved multiple photon interactions in a higher order process. It was the right family of physics. It was not the specific prediction from 1934. The fish leaped, but not quite from the same ocean Breit and Wheeler had described. The physics community celebrated E-144 as a genuine advance. Papers were written, results were analyzed. The experiment confirmed what the theory demanded. But the theorists and experimentalists who cared specifically about the pure Breit Wheeler prediction, the two real photons, nothing else, creating a pair in empty space, noted quietly and carefully that the specific case had not yet been tested. This distinction mattered, not for engineering purposes, not for practical applications. It mattered the way all fundamental verifications matter in physics. Because there is a difference between a theory that has been confirmed in spirit and a theory that has been confirmed specifically. The photoelectric effect was not just a nice demonstration of quantum ideas in general. It was a specific prediction that was specifically tested and specifically confirmed. The same standard applied to Breit and Wheeler. Their prediction was precise. Their conditions were specific. And until those precise conditions were met, the prediction stood as one of the longest unverified specific predictions in the history of physics. 63 years had passed since the paper was published. A man born the year Breit and Wheeler wrote their equations, could have lived a full life, raised a family, watched his grandchildren grow, and died peacefully in his sleep, all without seeing the prediction confirmed. The technology was improving, the lasers were getting stronger, the understanding of how to create and collide high-energy photon beams was deepening with each passing decade. New facilities were being designed. New detectors were being built. The conversation in the physics community was shifting from whether the pure Breit Wheeler process could be observed to when and how and by whom. The answer was taking shape in a building on Long Island, New York, at a facility dedicated to colliding heavy ions at energies that made the accelerators of the 1950s look like toys. A machine that could accelerate gold atoms, stripped of their electrons, to within a fraction of a percent of the speed of light, and slam them past each other in a controlled dance of electromagnetic fields. Not to smash the gold ions together, not to create nuclear debris, but to use the gold ions as a source of the most intense electromagnetic fields achievable in any laboratory on Earth. Fields intense enough to produce real photons in numbers and at energies that would finally, after 87 years of waiting, be sufficient to test the prediction that two young men had written down in 1934 and then quietly admitted they did not believe anyone would ever be able to check. The fish was about to leap. Almost everyone in the field could feel it coming. The papers describing the experimental strategy had been circulating for years. The detectors had been refined. The analysis techniques had been developed. The collaboration of hundreds of physicists from dozens of institutions had spent years preparing for a measurement that required extraordinary precision and extraordinary patience and extraordinary confidence that the theory they were testing was correct. But the confirmation had not yet arrived. The specific experiment had not yet produced the specific result. The prediction was still a prediction. Breit and Wheeler were still waiting. In whatever quiet corner of the universe holds the unverified claims of careful scientists, to be told that they were right. The universe had been running this process since its first moments. Near black holes, in the cores of gamma-ray bursts, in the blazing radiation fields surrounding the most violent events in cosmic history, photons had been colliding and producing matter for as long as time had existed. The process did not need human confirmation to be real. The fish had been leaping in the wild ocean of the universe since before any ocean existed on Earth. But science is not just about what the universe does. Science is about what human beings can demonstrate, measure, verify, and understand with the tools they have built. And the tools, finally, were ready. Somewhere in a detector the size of a house, surrounded by sensors and cables, and the quiet hum of machinery cooled to temperatures colder than deep space. The data was accumulating. The collisions were happening. The gold ions were sweeping past each other at incomprehensible speeds, their electromagnetic fields briefly overlapping, their photon clouds briefly meeting. And in that meeting, in that overlap, in that brief, violent crossing of two electromagnetic storms in the space between two nearly light-speed gold atoms, something was about to appear that had never been directly created from pure light in any human laboratory. The confirmation was 3 years away, but it was coming. There is a place on Long Island, in the state of New York, about 60 miles east of Manhattan, where the ground hides something extraordinary. From above, from a satellite image or a low-flying plane, you would see a wide, flat campus of buildings and roads, surrounded by the quiet green of the surrounding countryside. Administrative offices, research facilities, parking lots, the ordinary architecture of a working institution. Nothing about the surface of this place announces what is happening beneath it and within it. But underneath and around and through that campus runs a ring, a circular tunnel nearly 4 kilometers in diameter, lined with superconducting magnets cooled to temperatures colder than the surface of Pluto. Inside that tunnel, 2 beams of particles travel in opposite directions, accelerated by precisely controlled electromagnetic fields to velocities so close to the speed of light that the difference between their speed and light speed is almost too small to express in ordinary language. At certain points around the ring, these 2 beams are steered toward each other and made to cross. And at the crossing points, detectors the size of houses wait with extraordinary patience and extraordinary sensitivity for something to happen. This is the relativistic heavy ion collider at Brookhaven National Laboratory, RHIC, as it is known to the physicists who work there. It was built to study the conditions that existed in the first microseconds after the Big Bang, when matter was so dense and so hot that individual protons and neutrons had not yet formed, when the universe was a soup of quarks and gluons moving freely in a state of matter that has no equivalent anywhere in the present-day universe, except inside this machine. But in 2021, the RHIC collider and the physicists using one of its detectors, a detector called STAR, which stands for Solenoidal Tracker at RHIC, announced something that had nothing to do with quark-gluon plasma and everything to do with a prediction written on paper in 1934. They had seen the Breit Wheeler process, the pure version, the one that Breit and Wheeler themselves had believed would never be observed. Real photons, nothing but light, colliding with each other and producing matter from that collision alone. The announcement was not made with fanfare. It was published in Physical Review Letters, one of the most respected journals in physics, in a paper authored by hundreds of collaborators from institutions across the world. The language was careful and precise, the way physics papers always are. But underneath the careful language, underneath the precise statistical analysis and the systematic uncertainty estimates and the comparison between observed distributions and theoretical predictions, was something that deserved to be announced from the top of every building in the world. Human beings had, for the first time in the history of our species, taken light and made it become matter. Let me tell you how they did it. Breit and Wheeler's original prediction required 2 gamma-ray photons colliding in empty space. Getting gamma-ray photons intense enough and directed precisely enough to collide with each other in useful numbers was the technological challenge that had frustrated experimentalists for nearly 9 decades. The STAR collaboration found a way around this challenge. not by cheating, not by approximating, by using a source of real photons so intense and so well characterized that the original conditions of the prediction could be satisfied in a way that was both practical and experimentally clean. The source was gold. Gold atoms, stripped of all 94 of their electrons, reduced to bare gold nuclei, carrying a charge of positive 79 units, injected into the RHIC accelerator and pushed to nearly the speed of light. At the speeds achievable by RHIC, the gold ions were traveling at approximately 99.995% the speed of light. The difference between their velocity and the velocity of light itself was so small that light itself could only outpace them by a margin that would be difficult to measure with any ordinary instrument. Now here is the piece of physics that makes everything possible. When a charged particle moves, it carries an electromagnetic field with it. You already knew this in the abstract sense, because you know that electric charges produce electric fields, and moving charges produce magnetic fields. But what happens to those fields when the particle carrying them is moving at nearly the speed of light is something that our ordinary intuition does not prepare us for. The fields compress. They flatten. A charged particle at rest has an electromagnetic field that spreads out in all directions roughly equally, like the surface of a sphere surrounding a central point. But as the particle accelerates toward the speed of light, the field compresses in the direction of motion and spreads outward perpendicular to it. The sphere stretches into a disk, a thin, flat pancake of electromagnetic field traveling with the particle, extending far out to the sides while being squeezed nearly flat in the direction of travel. At 99.995% of the speed of light, the electromagnetic field surrounding a gold nucleus is compressed into something that physicists describe as a virtual photon cloud. This language carries real meaning. The compressed electromagnetic field surrounding an ultra-relativistic heavy ion, which is the formal name for a gold nucleus moving this fast, is mathematically equivalent to a dense cloud of real photons. Not almost equivalent. Equivalent in the precise quantitative sense that the calculations using the photon picture and the calculations using the field picture give identical predictions for any measurement you could perform. The virtual photon clouds surrounding these ions contain photons across a wide range of energies, including photons in the energy range required by the Breit Wheeler threshold, real enough to collide, real enough to produce electrons and positrons, real enough to satisfy, in the most rigorous mathematical and experimental sense, the conditions that Breit and Wheeler wrote down. When two gold ions are fired past each other, not colliding directly, because a direct collision of gold nuclei produces an entirely different and much messier kind of physics, but passing close enough that their photon clouds overlap, the photons from one cloud meet the photons from the other cloud in the space between the ions. And in that space, in that brief overlap of two electromagnetic storms traveling in opposite directions at nearly the speed of light, photons collide. Two photons, real photons, each carrying sufficient energy, meeting head-on, their combined energy exceeding the threshold that Breit and Wheeler calculated 97 years earlier. And from that meeting, in the empty space between two gold ions that never touch each other, an electron and a positron appear. The star detector sees them. They are produced with no net momentum along the beam direction, which is exactly what the Breit Wheeler process predicts. They are produced in back-to-back pairs, the electron going one way, the positron going the other, in a pattern consistent with the angular distribution that falls out of the quantum electrodynamical calculation of photon-photon collisions. The distribution of their combined mass matches the theoretical prediction. The rate at which they are produced matches the theoretical prediction. Every measurable property of these electron-positron pairs is consistent with one and only one explanation. Two photons met in empty space, they vanished, and an electron and a positron appeared where the photons had been. Light became matter. Now stop. Just stop here for a moment. Lie still wherever you are. Feel the surface beneath you. Feel the weight of your body distributed across the mattress or the sofa or whatever quiet place you have found for this hour. And let the weight of what just happened in that detector land on you the way the light from the screen is landing on your face right now. Human beings aimed light at light, in the space between particles that never touched each other, in a gap of empty space where there was nothing. Light collided with light, and matter appeared. Not rearranged matter, not matter that was hiding somewhere nearby and got knocked loose. New matter. Electrons that did not exist one moment and did exist the next, born from two photons that ceased to exist in the same moment the electrons came into being. The thing that every intuition you have ever had about reality told you was impossible happened in a detector in New York. And it has been happening, as we will come to understand, everywhere in the universe for as long as the universe has existed. But stay with the laboratory result for a little longer, because there is something about the conditions of this experiment that connects it to you, lying here, in a way that deserves to be spoken aloud. The light from the lamp beside your bed, if it exists, is producing photons right now. Ordinary visible light photons, with energies far below the Breit Wheeler threshold, each one carrying perhaps 2 electron volts of energy. The threshold for producing an electron-positron pair requires over 500,000 electron volts per photon. The lamp photons are softer by a factor of 250,000. They could not, even in the most favorable collision geometry, produce a pair. They are too gentle. But gentleness is not a fundamental property of light. It is a property of this particular source, at this particular intensity, at this particular moment. The photon from your lamp and the photon that Breit and Wheeler described are the same kind of thing. They are both excitations of the electromagnetic field. They are both governed by the same equations. The difference between them is not categorical. It is quantitative. It is a matter of energy, of intensity, of frequency. Given enough energy, given the right conditions, the light from every lamp and every star and every screen in the universe contains within itself the latent capacity to become matter. The seed of electrons is in the sunlight falling through your window. The seed of positrons is in the glow of the screen in your palm. Not the electrons that will appear from those specific photons under those specific conditions, because the conditions are wrong, the energies are too low. But the capacity, the built-in potential, the fact that photons and electrons are not categorically different things but different expressions of the same underlying field interactions, different faces of the same reality, means that given the right conditions, any photon can become matter. The sun, 93 million miles away, is pouring 3.8 times 10 to the 26 watts of energy outward in every direction. Each second, the sun produces more energy than all of human civilization has produced in its entire history, multiplied by a number too large to read aloud without losing the audience. That energy travels outward in the form of photons, an incomprehensible flood of photons. And each one of those photons, in principle, in the right conditions, carries within it the possibility of becoming the seed of physical matter. The sunlight on your skin right now is, in the deepest sense, a rain of potential matter. The photons striking you are not making electrons because the conditions are wrong, but they are, each one of them, governed by the same mathematics that governs the photons in the star detector that did make electrons. The process that happened in that detector is not alien to ordinary light. It is what ordinary light would do, what it can do, what it is permitted by the laws of physics to do, if you give it enough energy and the right meeting partner. Light becomes matter. Say it one more time, not as a surprising fact, but as something you are beginning to feel in your chest. Light becomes matter, and again, with the weight of everything we have covered tonight behind it. Light becomes matter. This is not a metaphor. This is not an approximation. This is not a philosophical claim dressed up in the language of physics. This is a measurement. This is data. This is electrons appearing in a particle detector on Long Island in a pattern that can be explained in one way and one way only. Two photons collided in empty space. Matter was born from the collision. The prediction made by two young physicists in 1934 was correct in every particular, and the universe was finally caught doing what it had been doing since before the Earth existed. Now, let us complicate the moment. Because the detection of the Breit Wheeler process in a laboratory in 2021 is the scientific confirmation of something, but it is not the discovery of something new about what the universe does. The universe did not start performing this process because human beings confirmed it. The universe has been doing it since its first moments. We confirmed a truth that was old before our sun was born. Consider the environments where this process is most active. Consider the places in the universe where light is dense enough and energetic enough that photon collisions producing matter are not rare laboratory events, but the dominant physics of the local environment. Consider a black hole, not the gentle center of a modest galaxy, but an active one, a quasar, a blazar, a feeding supermassive black hole at the center of a galaxy, billions of light years away, consuming matter at a rate that releases more energy in a second than our sun will release in its entire 10 billion year lifetime. The region surrounding this black hole is filled with radiation, not the gentle visible light of a bedroom lamp, hard radiation, gamma rays, X-rays, a field of photons so dense and so energetic that a human being transported there would be vaporized before the thought of survival had time to form. In this environment, photon collisions are not rare. They are constant. They are one of the primary mechanisms by which matter is continuously created in the most extreme environments the universe contains. Electrons and positrons are being born from light around black holes right now. The Breit Wheeler process is running continuously in those environments, pair after pair, appearing from the collision of gamma rays in the blinding radiation fields surrounding the most violent objects in existence. The fish is leaping constantly, everywhere in the ocean near a black hole, in numbers too large to count. Consider the gamma ray burst, the most energetic single event the universe produces, more energetic in its peak emission than the entire rest of the observable universe combined, created when a massive star collapses or when two neutron stars merge and release their energy in a focused beam of gamma radiation lasting seconds to minutes. In the fireball of a gamma ray burst, photon densities and energies are so extreme that pair production is not a side process. It is a defining feature of the physics. The fireball is partly made of electrons and positrons, continuously created and annihilated and recreated from the gamma radiation filling it. Matter and light are in a constant state of mutual conversion. The pairs appearing from light, annihilating back into light, and the light being energetic enough to produce more pairs in a cycle that shapes the entire structure and evolution of the burst. Consider the early universe. Not the universe of stars and galaxies, not even the universe of atoms and molecules, but the universe of the first microseconds after the Big Bang, a time when the temperature and density of the cosmos were so extreme that the conditions around a black hole, the conditions inside a gamma ray burst fireball, would have seemed mild by comparison. The entire observable universe, all 100 billion galaxies and all the space between them, compressed into a volume smaller than a grapefruit. Temperature measured not in thousands or millions, but in trillions of degrees. Every cubic centimeter of space containing more energy than the most energetic event our modern universe can produce. In this environment, light and matter were not two separate things at any moment. They were a single, seething mixture, constantly interconverting. Electrons and positrons being created from photons and annihilating back into photons, and the photons colliding to produce more electrons and positrons, in a cycle that defined the nature of reality at that moment. The universe was not yet a place where light and matter could be separated and labeled. It was a place where the separation had not yet formed, where the wall had not yet been built, where the shining things and the solid things were still one churning ocean. As the universe expanded, it cooled. As it cooled, the photons became less energetic. The temperature dropped below the threshold where spontaneous pair production from photon collisions was common. And then something happened that physicists still argue about and do not fully understand. Something that may be the deepest unanswered question in all of cosmology. Matter and antimatter are produced in equal numbers by the Breit Wheeler process, one electron and one positron, balanced exactly. If the early universe produced matter and antimatter in perfectly equal numbers from its primordial sea of photons, then every electron produced would have had a positron partner, and every proton would have had an antiproton partner. And when the universe cooled enough, that pair production stopped. All of those particles and antiparticles would have found each other, annihilated, and converted back into photons. The universe would have ended as pure radiation. No matter, no atoms, no stars, no planets. No you lying in this quiet room listening to these words. But you are here, which means the balance was not perfect. Somewhere in the first moments, for reasons that physics has not yet fully explained, matter won by a tiny margin. For every billion antiparticles, there were 1,000,000,001 particles. When the annihilation was complete, the billion pairs had converted back into photons, adding to the radiation filling the young universe. And the one remaining particle in each billion survived, unpaired, uncancelled, the residue of a broken symmetry. Every atom in your body is one of those survivors. Every electron orbiting every nucleus in every molecule of your skin and your blood and your brain is a descendant of a particle that escaped the primordial annihilation because there were ever so slightly more particles than antiparticles in the first moments of time. You exist because of an asymmetry so small it amounts to 1 part in 1,000,000,000. You exist as the leftovers of a universe that tried to erase itself and almost succeeded. And the matter that survived, the matter that became the hydrogen atoms of the first stars, the carbon and oxygen forged in those stars, the atoms that assembled themselves into the molecules of your body over billions of years, that matter was not made from prior matter. In the most fundamental sense, it was made from light. From the photon collisions of the first moments, from the Breit Wheeler process running at scales and temperatures we cannot reproduce and cannot fully imagine, everywhere in the young universe simultaneously, you are, in the most literal sense that physics permits, made from light that became matter, not descended from matter that was always there, not assembled from pre-existing ingredients, made from photons, from excitations of the electromagnetic field, from the same stuff that is touching your face from the screen right now, only unimaginably more energetic, unimaginably more dense, and meeting in a universe whose entire existence was contained in a space smaller than anything you have ever held in your hand. Light becomes matter, the lamp becomes the nightstand, the photon becomes the electron, the shining things become the solid things, and the solid things, given enough energy and the right conditions, become shining things again. The conversion runs in both directions, always, everywhere, from the first microsecond of the universe to the detectors at Brookhaven to the quiet room where you are lying now. The wall you began this night believing in, the wall between light and matter, between the seen and the touched, between the shining things and the solid things, is not a wall. It never was. It was a doorway that the universe has been walking through in both directions since before time had a name. And now, finally, human beings have watched it happen. We have aimed our instruments at the right place, at the right moment, with the right patience, and we have seen the fish leap from an ocean that, 97 years ago, 2 young men predicted it would leap from. We were right. The mathematics was right. The universe was right all along. We just needed the tools to see it. What remains now is not a question about whether this happens. We know it happens. What remains is the question that every genuine scientific confirmation opens rather than closes. The question of what it means for the universe, for matter, for light. For you lying here, made of the survivors of a broken symmetry, built from the aftermath of photons that became matter in the first moments of everything. That question is not answered tonight. It is given to you to carry into sleep, to let your mind move around in the hours before morning, not as a problem to be solved, but as a new kind of seeing, a new way of looking at the lamp and the nightstand and your own hand resting on the blanket, a new way of understanding what you are. Come back now. Come back from the particle detectors and the gold ions and the gamma-ray bursts and the first microseconds of the universe. Come back from all of that vast and violent physics and return to where you are, to the specific quiet of this specific room, to the particular darkness or half-light surrounding you right now, to the weight of your body, settled and still, the slow rhythm of your breathing, the soft pressure of the surface beneath you holding you up the way it always has, the way it will continue to do while you sleep. You have traveled a long way tonight. You began in the comfortable world where light and matter were 2 separate things, where the lamp and the nightstand belonged to different categories of existence, where the shining things and the solid things had their own territories and their own rules and their own permanent separation. You have passed through the patent office in Bern and the double-slit experiment and the trembling quantum vacuum and the paper that 2 young men wrote in 1934 and the particle detector in New York that finally confirmed what they had written. You have been to the edge of black holes and inside gamma-ray bursts and back to the first microsecond of everything that exists. And now you are here, in a bed or on a sofa or in a chair, in a room that has a lamp or a screen or a sliver of streetlight coming under the door, in a body that is breathing without being asked to breathe, that is warm without being asked to be warm. That is alive in the uncomplicated and extraordinary way that living things are alive in the middle of the night, when no one is paying particular attention to the miracle of it. Let us stay here for a while. Let us not rush away from this room, because this room, this body, this quiet, ordinary moment is where the physics we have been exploring all night finally arrives at its destination. Not in the laboratory, not in the equations. Here, in you. Look at your hand, or imagine looking at your hand if your eyes are closed. The hand resting on the blanket, or curled near your face, or lying open on the pillow beside you. A hand you have had your entire life. A hand so familiar that you almost never see it anymore, the way you almost never see the walls of a room you have lived in for years. A hand made of skin and bone and blood and nerve, made of cells containing molecules containing atoms, 100 trillion atoms or thereabouts, each one a nucleus orbited by electrons, each one almost entirely empty space with a tiny dense center and a cloud of probability surrounding it, where the electrons might be found if you looked carefully enough. Those atoms are old. That is the first thing to understand about them. They are not new. They were not made when you were born. They were not assembled for you specifically. They have been moving through the world for an almost unimaginable length of time, passing from one form to another, from one body to another, from one kind of matter to another, since long before the earth existed, and long before the sun existed, and long before the galaxy in which the sun sits had finished forming itself from the collapse of a primordial cloud of gas. The hydrogen atoms in your body, and hydrogen is the most abundant element in a human being by number of atoms, were made in the first 3 minutes after the Big Bang, not in stars, not in explosions. In the hot, dense plasma of the very early universe, when temperatures had fallen just enough to allow protons and neutrons to briefly combine into the first atomic nuclei, hydrogen, some helium, a trace of lithium. These were the raw materials the universe started with, and some of the hydrogen atoms that formed in those first 3 minutes have been moving through the universe ever since, passing through gas clouds and stars and planets and oceans and living cells and the bodies of creatures that had no names because no one had yet evolved to give them names. And now some of those atoms are in your hand, in the water that makes up most of your body, in the molecules of your blood, in the cells of your skin. Your hand is partly made of matter that is 13.8 billion years old. The carbon in your body, the element that forms the backbone of every organic molecule, every protein, every strand of DNA, every cell membrane, was not made in the Big Bang. The early universe did not produce carbon in significant quantities. Carbon is a more complex atom, requiring conditions that the early universe briefly had and then left behind before the heavier elements could form. Carbon was made in stars. In the cores of stars much larger than our Sun, where temperatures and pressures are high enough to fuse helium nuclei together into carbon nuclei, 3 at a time, in a process called the triple alpha reaction. These stars burned for millions of years, fusing their way through their nuclear fuel, building up carbon and oxygen and nitrogen and the other elements that life requires. And then they died. They exhausted their fuel, lost the battle against gravity that every star is always fighting, and collapsed and exploded in the violence of a supernova, scattering their accumulated elements outward into the surrounding space. The carbon in your body was forged inside a star that died before our sun was born. The explosion that killed that star scattered its carbon across a region of space that eventually, billions of years later, collapsed under gravity into a new cloud, a new star, a new system of planets, our sun, our Earth. And on that Earth, over billions of years, that scattered carbon assembled itself into molecules and cells and organisms, and eventually into the particular arrangement of matter that became you. You are, in a very precise and non-metaphorical sense, made of stardust. This is not a poetic phrase, though it is a beautiful one. It is a statement of nuclear physics and stellar evolution. The carbon and oxygen and nitrogen in your body have a documented history that includes the interiors of at least one and probably several generations of stars that lived and died before our solar system existed. But we can go deeper than that. We can go further back, because the story of where your atoms came from does not start in the stars. The story starts before the stars. It starts before atoms. It starts in a place and time where the distinction between matter and energy was not yet settled, where the photons and the electrons had not yet decided to be separate things, where the universe was still in the process of becoming the universe we live in, still running the conversion that we have been tracing all night, still transforming light into matter, in the hot and violent first moments of everything. The protons in the nuclei of your atoms, the electrons orbiting those nuclei, the neutrons packed alongside the protons. Every fundamental particle of matter in your body has an origin that traces back to the primordial fire, to the time before atoms, to the time when the Breit Wheeler process and related particle creation processes were running everywhere simultaneously, in a universe that was nothing but energy converting itself into matter, and matter converting itself back into energy, in a cycle so rapid and so total that the word cycle barely captures it. It was not a cycle, it was a state in which light and matter were not two things but one thing in two phases, like water and ice, like liquid and solid, like the same substance expressing itself differently depending on the local conditions. And then the universe cooled, and the conversion slowed, and matter won by a fraction of a fraction. And the survivors, the unpaired particles that had no antiparticle to annihilate them, drifted apart as the universe expanded, eventually clumping under gravity into the first gas clouds, the first stars, the first nuclear furnaces that would build the heavier elements. And those elements scattered, and they clumped again, and they scattered and clumped across billions of years and billions of light years until eventually, in a process so complicated and so slow that no human mind can fully hold it, they arrived in the configuration you are lying in right now. You are the universe examining itself. You are matter that began as light, that passed through the cores of multiple stars, that rode the shock wave of at least one stellar explosion, that drifted through interstellar space and condensed into a planet, and dissolved into an ocean, and assembled into a cell and divided and divided and divided across geological time until it became a nervous system capable of understanding its own history. You are not in the universe. You are not separate from the universe, looking at it from the outside. You are the universe. A local arrangement of the same matter and energy that has always been here, reorganized into a form complex enough to wonder about its own origins. And those origins, as we have now traced them all the way back, begin in light. Think about what this means for the separation we started with tonight. The comfortable belief that there were two kinds of things in the world, the shining things and the solid things, the light and the matter, the seen and the touched. We have followed that belief back through history and watched it erode, layer by layer, through Newton and Young and Einstein and Heisenberg and Breit and Wheeler and the star collaboration at Brookhaven. And what we have arrived at is not a correction of the old belief. It is a dissolution of it. The categories themselves were the mistake, not the specific answer assigned to each category, but the existence of the categories at all. Light and matter were never two things. They were always one thing wearing two faces. Energy wearing the face of radiation in one moment and the face of mass in the next. The electromagnetic field wearing the face of a photon when it is traveling and the face of an electron when it has been anchored into a standing excitation. The universe wearing the face of fire in its first moments and the face of solid matter in its current age, and eventually, in the long future, when the last stars have burned out and the last protons have decayed, wearing the face of radiation again as everything returns to the field from which it came. The wall between the seen and the touched was never a wall. It was always a doorway, and matter and energy have been walking through it in both directions since the first moment of time, and they will continue walking through it until the last moment, whatever that turns out to be. Now look up, or imagine looking up, toward wherever the sky is from where you are lying. Above the ceiling, above the roof, above the thin shell of atmosphere that holds the air you are breathing. The night sky is doing what it always does in the darkness. It is radiating. It is full of light, traveling in every direction from every source at every distance. And some of that light is reaching you right now. The photons from distant stars passing through your window or your walls, traveling through the room where you are lying, passing through your body without interaction, because the energies involved are not high enough and the cross-sections are too small. A rain of starlight passing through you constantly, all night, every night, without your knowing it. Some of the stars whose light is reaching your room right now no longer exist. They burned out thousands of years ago, in some cases millions of years ago, but the light they emitted before they died is still traveling outward through space, still carrying the energy of those long-dead fires, still crossing the distance between where those stars were and where you are now. You are being touched by the light of stars that are already gone. You are, in a sense, receiving messages from the past, photons that left their sources before your ancestors existed, before your species existed, before the planet you are lying on had cooled enough to hold an ocean. That light is real. Those photons are real. And those photons, in the right conditions, in an environment, with the right energy density and the right collision geometry, could become matter. Not the specific photons crossing your room right now, because the energies are wrong and there is nothing for them to collide with, but the same kind of thing, the same excitations of the same field, governed by the same equations that were satisfied in the star detector. The starlight coming through your window is, in the deepest sense, the same kind of thing as the photons that became electrons in New York in 2021. Gentler, cooler, but the same kind of thing. You are surrounded by light that is one step removed from becoming matter, and your body is matter that is one step removed from having been light. The distance between you and the starlight outside your window is not the distance between two fundamentally different kinds of things. It is the distance between two phases of the same thing, two temperatures of the same substance, two expressions of the same underlying field activity that fills the universe from edge to edge and has been filling it since the beginning. You are part of this conversation. You have always been part of this conversation. The conversation between energy and substance, between the shining things and the solid things, between the photon and the electron, has been happening since the universe began, and it includes you. Not as a spectator, not as an observer standing outside watching the physics happen, as a participant, as a collection of matter that was once energy, that will one day be energy again, that is, right now, engaged in the slow process of being matter in the particular configuration that makes up a person lying in a quiet room at some hour of the night. You were never outside this. You were never separate from it. The old feeling of separation, the feeling that you were a solid thing in a world of solid things, occasionally illuminated by a different and separate kind of thing called light, was always an incomplete picture. Not wrong, the way a dream is wrong, but incomplete. The way a map that shows only roads is incomplete, without showing the rivers and the mountains that shaped where the roads were built. The complete picture is this. You are the universe doing what it has been doing since its first moment, converting energy into matter and holding it in form long enough for it to look at itself and wonder what it is. You are frozen light that has learned to ask where it came from. You are an excitation of the fields that fill space, a local arrangement of the quantum vacuum, a standing wave in the ocean that looks at the ocean and calls it something separate from itself. It is not separate. It never was. Now, let your eyes close, if they are not already closed. Let the weight of your body settle more deeply into whatever is holding you. Let the thoughts that have been moving through your mind tonight slow down, the way a river slows when it reaches the wide, shallow place before the sea. Let them spread out and become less distinct. Let the equations, and the experiments and the names and the dates soften into something less specific, into a feeling, into a new quality of perception that does not need to be held onto, because it is already part of you now, in a way that sleep will not erase. The lamp in your room, if there is one, is producing photons right now. Each photon is an excitation of the electromagnetic field, a ripple in the same ocean whose other ripples became you. The light is not separate from the matter of the lamp that produces it. The lamp is not separate from the room that holds it. The room is not separate from the earth. The earth is not separate from the sun, whose ancient light built the carbon in the wood of every tree that was ever burned to warm a house. And the sun is not separate from the universe that built it from the aftermath of photons becoming matter in the first moments of time. Everything in this room, including you, is one system, one conversation, one ancient process of energy finding form and form, releasing energy, and energy finding form again in the long, patient, endlessly inventive improvisation that is the universe working out what it wants to be. The glow of the screen you may be watching this on is the same old light, ancient in its physics, familiar in its equations, made of photons that carry in them, at the right energies and the right conditions, the capacity to become matter. The screen and your eyes looking at the screen are not two different categories of being. They are two arrangements of the same underlying reality, temporarily differentiated, temporarily distinct, moving through their temporary forms in the long story of energy that began before time had a name. The warmth of your skin in the dark, that warmth is energy, that energy is mass, that mass is you. And you are the universe holding some of its energy in a particular form for a particular time, the way the ocean holds a wave for the few seconds before it breaks and returns and becomes ocean again. You are a wave that has been traveling for 13.8 billion years. You are a long wave, and you are about to sleep, which is one of the kindest things a wave can do, to slow, to quiet, to let the turbulence settle, to return for a few hours to something closer to the ground state, the calm lake before the pebble falls, the field at rest before the excitation arrives. Sleep is not nothing. Sleep is the universe resting part of itself. Sleep is matter doing what matter does when it is not being organized into activity, returning to something quieter, something more like the field before the ripple, something that is not the absence of being, but a different mode of it. So let yourself go there. Let the physics dissolve into the feeling. Let the equations and the experiments and the names become the background hum they have always been, the constant trembling of the quantum vacuum beneath everything. Present whether you are thinking about it or not. Let the conversation between energy and matter continue without your conscious participation for these next few hours, because it will continue. It does not need you to be awake. It was running before you were born, and it will run after you are gone, and it is running right now in every atom of your body, whether you are asleep or awake or anywhere in between. You are not watching the universe from outside it. You are the universe, and you are going to sleep now. And somewhere above you, through the ceiling and the roof and the thin, bright shell of atmosphere, the starlight is still falling. Photons that left their sources years and decades and centuries ago, still traveling, still carrying the energy of long-dead fires, still crossing the dark between here and there, reaching your window, passing through your room, passing through you, continuing outward into the dark beyond. Some of that light, in the right conditions, could one day become matter, could one day slow down and take form, the way the light of the early universe slowed down and took form, could one day be part of something that breathes and wonders. For now it is still light. For now it is still traveling. For now it is still the shining face of the thing that also has a solid face, the other form of the substance that is currently lying in a quiet room, breathing slowly, growing heavy, carrying into sleep the extraordinary and simple truth that it has always been, in the most fundamental sense that physics can confirm. One thing, not two things, not light over here and matter over there. One thing, ancient and continuous and present in everything you are and everything you touch and everything that touches you in the dark. One thing. Sleep now.